Number 1 says, which of the following compounds best matches the IR spectrum given below? So in this video, I'm going to go over some of these, all of these questions, and basically there's a few things you can find in the bottom description below. So what you're going to do is, if you look in the description, you can find a copy of these questions, a copy of the written out answers, and a copy of the times for each of the questions. So if you click on any of those individual times, you can watch that question. So I'm going to go ahead and get started here. It says, which of the following compounds, as I already said, best matches the IR spectrum given below? So the first thing I'm doing is I'm looking for functional groups that I could see here on these different compounds. So I see aromatic CH, I see non-aromatic CH all over the place. I see C double bond O, and I see OH. So these are essentially what I'm going to look for. I'm going to start over here just because that's where I happen to start on this one. And I'm going to notice that there's no broad peak here, so there's no OH. Here I have CH aromatic. Here I have CH non-aromatic or aliphatic. And here I'll notice that I have no, around 1700, C double bond O. So it can't be this one, or this one, because there's no OH and there's no carbonyl group. There is aromatic and non-aromatic CH, aromatic and non-aromatic CH, which lets me know that this is choice letter D. Question 2 says, which of the following compounds best matches the proton NMR spectrum given below? So one thing that I instantly notice about this NMR spectrum is that we have some ring protons, and in fact we have 5 ring protons. Well, since the ring contains 6 protons total, if it's just benzene, right, C6H6, then if there's 5 protons, that likely means there's a single substitution. Probably not 2 substitutions. The other thing is, if we look at naphthalene, which can be a little bit complicated, these are all aromatic protons, and we clearly have some non-aromatic protons here. So I've essentially eliminated these 2 choices. The only 2 choices I have left are this one and this one. And these ring protons could explain the protons here, but then there should be these protons only left. But that's not what I see. I see 2 more groups of protons. And here I have 2 H's here and 3 H's here, which are explained well here. This is a quartet, which is explained well here because there's 3 protons on the adjacent carbon. And this is a triplet, these 3, because there's 2 protons on the adjacent carbon. So molecule D is clearly the best choice for this proton spectrum. So notice that it's a combination of looking at the spectrum and looking at the choices. So I'm not looking at the spectrum only independent of the choices. I'm kind of looking at both and comparing which ones it could and which ones it would not be. Number 3 says, identify the correct alcohol used in the following esterification reaction. So an esterification reaction is a reaction of a carboxylic acid and an alcohol. This is the carboxylic acid shown here, so acetic acid. Well, what's the alcohol? The alcohol is this one right here. The O from the ester does come from the alcohol, okay, and this one leaves as water, essentially. So this does come from the alcohol, but when you're looking at just trying to identify the alcohol, the carboxylic acid is here, the alcohol is here. So we have HO, then we have the same structure, so 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and we have a methyl group off of that last one, so we end up with this. And if we look at our choices here, that is choice letter C. So that's how we can break that apart. All right, number 4 is a safety question, so probably not too many people are watching this particular question. I do want to say about safety, safety questions tend to be relatively easy on tests because it's common sense. However, safety is like the most important thing in the lab. It is the most important thing in the lab. So even though they seem like easy gimme questions, that doesn't mean it's not important. So that's why we put it on the test. So it says, in order to neutralize traces of acid from your product mixture, you add sodium bicarbonate to the separatory funnel containing your product layer. While vigorously shaking the mixture, you forget to frequently vent the gas that is produced, so the stopper is ejected and the material splatters onto your face and safety goggles. What should you do? You should inform the TA, use the eye wash station or sink as needed to wash any chemicals off for 15 minutes, and seek medical attention as necessary. This is clearly the right answer, okay? Don't call your friend, run out in the hallway and yell, or this kind of stuff. This is gonna, again, be a fairly straightforward question, but that doesn't mean the safety isn't super important, because it's the most important thing. Number 5 says, the compound 2-hydroxybenzoic acid is shown below. It was dissolved in ether and then extracted with an aqueous sodium bicarbonate. I don't know if we need an, so just with aqueous sodium bicarbonate. The ether layer and the aqueous layer are placed into 2 different beakers. What is the product formed when 2-hydroxybenzoic acid reacts with sodium bicarbonate? Well, we have this dissolved in some organic solvent, ether, and we add NaHCO3 aqueous. What happens? This is baking soda, it's a base. This is a carboxylic acid, and this specifically is the acidic proton. So what are we going to do? Well, this proton is going to go to make H2CO3, and then Na is going to go with this. But don't write down H2CO3 yet. So we have C double bond O minus Na plus. This OH just goes along for the ride. Okay, it's still there. I guess I should have drawn this up and to the side, but it's the same thing. Then we ended up with H2CO3. H2CO3 is not stable, so it breaks up into CO2 gas plus H2O liquid. This is why it bubbles when you add sodium bicarbonate a lot of times into your separatory funnel. So this is basically what's happening. The real question is, what is the phase of this? It's not asked here, but this is the most important thing here. The phase of this is now aqueous. So this molecule was had a strong affinity for the organic solvent, but this molecule, now that it's ionic, has a strong affinity for the aqueous solvent, so this is aqueous. But to answer this question, this molecule and this molecule are the same, so the answer is choice letter C. Number 6 says, the 2 molecules below are dissolved in ether and placed into a separatory funnel. Which of the following would be a good solution to separate these 2 molecules? Well, what we need to do is we need to see if either of these 2 molecules are acid-base, and if they're not, they're neutral. So in organic chemistry, bases are amines. Acids are carboxylic acids, and for the most part, all other molecules are neutral. So this molecule only contains carbon and hydrogen, so it is clearly a neutral molecule. There's no acidic or basic parts of this molecule, right? It doesn't want to gain or lose protons. It only contains carbon and hydrogen. What about this? This is an amine, so this is a base. Notice that the ester is neutral. This is not an acid. If there were an H here, that'd be a carboxylic acid, then it would be an amino acid, which is a whole other thing. But this is a base because it contains an amine. The ester is not acidic. So if we want to extract this into the aqueous layer, we want to protonate this amine. Well, how do we do that? We add HCl. If we add HCl to this amine, so I'm just going to write it generally, if we have NH2 bonded to something, and we add HCl, what happens? This lone pair takes the proton, and we end up with NH3 plus Cl minus. All right, and this would be attached in this case to this ring in this ester group. Okay, so this would all be over here. I'm not going to draw all of it, but you get the idea. So this is now ionic, and it's soluble in the aqueous layer. So if we add an acid such as HCl, we can extract molecule B, the base, from the ether layer or into the aqueous layer. It's the same thing. So the answer here is choice letter B. So for question number 7, it's really a good idea to watch questions number 5 and 6 before you watch 7, because it's more of the same. It says the 2 molecules below are dissolved in ether and placed into a separatory funnel. Which of the following would be a good solution to separate the two molecules. So this is a ketone, so it is also neutral. It doesn't have any acidic or basic parts. This molecule is a carboxylic acid, so it's an acid. So what do we want to do? Well, we want to use a base to take off this proton, just like was shown in question 5, and then it'll make this ionic and soluble in the aqueous layer. So what's a base? HCl or sodium bicarbonate. Sodium bicarbonate is a base. So if we want to add sodium bicarbonate, it will extract the carboxylic acid from the ether layer and into the aqueous layer. So the answer here is choice letter B. Again, for more context, please watch questions 5 and 6. Number 8 says, which of the following is the strongest base out of the 4 molecules? Well, as discussed in question 6, amines are organic bases. This nitrogen of this amine is able to accept a proton, making it a base. This molecule is neutral, doesn't want to accept a proton, so it's not a very strong base. This molecule is an acid. It wants to donate a proton, so it's definitely not a strong base. And this molecule is neutral. It doesn't have a carboxylic acid functional group, so therefore it is not going to be very likely to accept a proton. So the molecule here that's clearly the strongest base is the amine, molecule A. Again, for more context, you could watch question number 6. Question 9 says, in the following fictitious reaction, 1.5 moles of A2 is reacted with 2 moles of B and 4.5 moles of C to form BC. What is a limiting reagent? Now in the actual answer key, I do all of the math here, but here I want to kind of do it from a logic perspective, just to how I would do it on a test if I was in the interest of time. Let's put it that way. So for every one A2 reacted, we make one BC. So it's a 1-to-1 stoichiometry, one here, one here. So this means this would give me 1.5 moles of BC. B and BC are also 1-to-1. So for every mole of this, I get a mole of this. So if I start with 2 moles of B, I'll make 2 moles of BC. In the case of C, it's a 2-to-1 relationship. So for every 2 of these, I make 1 of these. Said another way, if I start with 4.5 moles of this, I'll make half as many, or 2.25 moles of C. Well, which one gives me the least amount of, this should be BC. Which one gives me the least amount of BC? 1.5 moles is the least amount of BC, which makes A2 our limiting reagent. Question 10 says, in the reaction, 2.5 grams of product was isolated. If the theoretical yield was 8.4 grams, what is the percent yield? Well, the percent yield is equal to the actual divided by the theoretical times 100. So in this case, the actual is 2.5 grams. The theoretical is 8.4 grams, and we have to multiply by 100. When you do that math, you find that it is 29.8% yield. Choice letter C. Number 11 says, the next 4 questions are related to the reaction below. And specifically, they're all asking about the mechanism of the reaction below. So what I'm going to do is I'm going to write out the mechanism, and then once we have the mechanism, these 4 questions are easy to answer. So let's go ahead and look at this. We have here a 1, 2, 3, 4, 5 carbons, so 5 carbons. We have a methyl group and an OH here. We have a tertiary alcohol, okay? And we're going to react it in the presence of H plus with ammonium bromide, which is essentially just a source of Br minus, a nucleophile. So we're going to have a nucleophilic substitution. The question is it going to be SN1 or SN2? It's not going to be elimination here. So is it going to be SN1 or is it going to be SN2? Well, the first thing we need to notice here is that OH is not a very good leaving group. So what do we need to do? The first thing we need to do is we need to protonate it and make it into water, which is why we had the strong acid, and make this into water, which is a good leaving group, because it's a weak base, not a strong base. So we go ahead and do that, and we get OH2 with a plus charge. Okay. Now, this molecule has a choice, right? There's 2 things that could happen. The Br minus could come in and kick this out, or this could leave and form the carbocation. The way we determine which of the two things will happen is by looking at the carbocation that would form. So if this leaves, it'll form a tertiary carbocation. A tertiary carbocation is relatively stable compared to a primary or a secondary. So that's what happens. And we get water as the leaving group. Now Br minus comes in, attacks here, and what we end up with is the substitution, but through the carbocation mechanism. What type of SN reaction, what type of substitution reaction is this? Well, this is SN1. Why? Because the rate of this reaction, the slow step, is the formation of the carbocation. So it's the concentration of this, the carbocation forming species, that's important in the rate of the reaction. So the slow step is this. This carbocation will essentially react with the first Br minus that it bounces into. So in this case, we have an SN1 mechanism. Question 12 says, in the first step of the mechanism, which of the following is formed? Well, this is what was formed in the first step of the mechanism. We got the protonated water, which is molecule A here. Then it says, in the second step of the mechanism, which of the following is formed? Well, in this case, we formed this tertiary carbocation, which is molecule B. Again, once you have the mechanism, that's the hard part. Answering the questions once you have the mechanism is pretty straightforward. And then finally, what is the product of this reaction? Well, we end up with the brominated product, which is right here. Okay, so first of all, if you just realize this is a substitution reaction, you would remember that this is the brominated product. And the fact that it asks for both steps means that it has to be SN1, because the SN2 mechanism goes in a concerted step where the nucleophile attacks and the leaving group leaves at the same time. So that is basically how we would approach this problem. Number 15 says, rank the following molecules in order of strongest acid to the weakest acid. And I'm going to use A to identify what these are, and then I'm going to pick the right answer after that, so A is not the right answer. So in the first case, we have propanol and alcohol. Alcohols are very or extremely very weak acids. All right, this proton is a tiny bit acidic, but it's very, very weak. Next, we have an amine. So this is the same propyl group, and now we have an amine. Amines, as we've talked about previously, are bases. And the last one is we have C double bond O bond OH. This is an organic acid. Organic acids are weak acids. So it's interesting because an organic acid is a weak acid, but among these choices, it's the strongest acid. So the carboxylic acid is the strongest acid. The alcohol is very slightly acidic. It's a very, very weak acid. And the amine is actually a base. So this is the order of these particular things based on the functional groups that are provided. Question 16 says, a mixture containing the molecule below is dissolved in the organic layer. An aqueous solution containing blank should be used to extract the compound from the organic layer. So this is an amine, an organic base. So if this is dissolved in organic solvent, I'm going to pick ether, and we add an acid, HCl aqueous, what happens? Well, this lone pair grabs that proton. And what we end up with, is NH3 plus bonded to the ring, like so, and then bonded to the C double bond O bond CH3. It's a methyl ketone. All right, this is plus, and we end up with Cl minus. But where would we find this? This is now ionic, so it has no affinity for the ether, so we would find this in the aqueous layer. At the end of the day, adding an acid, like HCl, which is the only choice here that's an acid, is what's going to remove this from the ether layer. All right, so now we have question number 17, which is similar to question 1. It says, which of the following molecules is consistent with the given IR spectrum? So we want to do a combination of things. We want to look at the molecules that we have, and we want to look at the IR spectrum. And you kind of can't do these independently of each other. So one thing I notice is we have aromatic CHs, Okay, we have non-aromatic CHs. We have a C double bond O, this is an aldehyde, and this one has just aromatic CHs. So what can we find here? Well, first thing I notice, for whatever reason, is there's no strong peak around 1700, so there's no C double bond O. That eliminates this as a choice, so this can't be an aldehyde. All right, the next thing that I notice is we have a CH aromatic and a CH non-aromatic. So that eliminates this choice because it only has aromatic CHs. So now I'm down to these two. So even if you're not sure where the NH2 comes from or where it would be, there is something outside of the fingerprint region that's here that we have yet to identify. And this happens to be the NH, okay, which lets us know that this is molecule A. I do want to point out, you'll notice that I ignored everything down here. So we're not looking at that. That's called the fingerprint region, and we can expect that, that's unique for this molecule. However, we're not going to be able to identify much. So that's how I worked my way through question number 17. Question 18 says, of IR and proton NMR, which will better distinguish the two isomers below? Well, the first thing is, are these things isomers? This one is C6H14O, 6 carbons with an alcohol group. This one has 5 carbon chain, a 6th carbon, and an alcohol group, so it is also C6H14O. So they are isomers, so that's not the answer. Now, which will better distinguish them? Well, let's look what we have. We have CHs that aren't aromatic and OHs. So this will give us a broad peak, somewhere around 3,400. This will give us the peaks just below 3,000. That's about all we're going to be able to see. But what about IR? Well, NMR. In the case of NMR, these protons are unique. These protons are unique. These protons are unique. These protons are unique. And that proton is unique. But we're going to have an integration 6 here, and it's not going to have any splitting. In this case, this is unique. This is, this is, and this is. All right, now down here, these are going to be pretty close together, but they are going to be actually unique. And you're certainly not going to see a singlet with an integration of 6. So in this case, NMR will easily distinguish these molecules, IR not so much. So you may ask, well, NMR will almost always distinguish molecules. When is IR useful? Well, in a lot of the reactions you've done in this course, you've changed the functional group. If you change the functional group, IR can be very useful because you can actually see a difference in the functional group. Also, IR is a lot faster to perform, usually, and furthermore, it requires a significantly less expensive instrument. 19 says, identify the major product of the following Friedel-Crafts acylation reaction. So in this case, we have acetyl chloride and aluminum chloride. And you may recall that the aluminum chloride takes off this chlorine and makes the acylium ion with a positive charge here. The acylium ion then attacks the ring in an electrophilic aromatic substitution reaction. We lose an H to resume aromaticity. So essentially, at the end of the day, what we do is we add the acylium ion to the ring. Here is the acylium ion added to the ring, and we get molecule A as our answer. Number 20 says, which of the given molecules is best represented by the proton NMR spectrum below? So one thing I notice is we have 5 ring protons, which usually means we have a mono-substituted ring. So we have something that isn't ring proton, so it's not this one. So it could be this one, or this one. Now let's take a look. Other than the ring protons, we have an OH, okay, which will just give us a singlet, and it'll be small. It'll have an integration 1. That can't be it. What about this one? In this case, we should have a peak with 2 H's here, which should be a quartet, and 3 H's here, which should be a triplet. So we should have something with an integration 2 and a quartet because there's 3 adjacent protons. And in this case, an integration 3 with a triplet because there's 2 adjacent protons. I don't see anything like that. In this case, I have CH3, CH3. They're not split, they're chemically equivalent. So we get this large singlet with an integration 6, which tells us that this is molecule C. Again, as I've done in several other examples, we're kind of looking at both. We're looking at the spectrum, in this case the NMR, and the molecules at the same time and trying to think about what's going on. Number 21 is a Le Chatelier's principle question. It says, given the following fictitious reversible reaction, which will drive the reaction towards the reactant's side? So in this case, we need to look at what is Le Chatelier's principle. So Le Chatelier's principle basically says that a reaction will shift to reestablish equilibrium. So for example, if we add more reactant, the reactant will shift towards the product to get rid of that reactant. If we add more product, the reaction will shift towards the reactants in order to get rid of that product. And it works the other way as well. If we reduce some amount of reactant, the reaction will shift to make more reactant. And if we reduce some amount of product, the reaction will shift to make more product. So let's take a look. Add more A2. If we add more A2, that means A2 increases and the reaction shifts to the right to get rid of the A2. So it shifts towards the products. That's not the answer to this question. Remove some B. If we take B away, now the reaction shifts towards the reactants to reestablish equilibrium. So in this case, it shifts to the left, and that's an answer to the question. And then remove some BC. If the amount of BC goes down, the reaction says, hey, there's not enough BC. It shifts to make more BC, which in this case, because BC is a product, it shifts towards the product. So we found the answer. It's removing some B. It's clearly not A and C, and it's clearly not none of the above. Number 22 says, what are the formal charges on the starred atoms from left to right? Well, remember that when we're doing formal charge, we count the bonds as one each, and we count the lone pairs as one each, because the bond has 2 electrons in it, but one belongs to nitrogen, and in this case, one belongs to the carbon of the methyl group. How many electrons, valence electrons, does nitrogen have? Well, it's in group 5A, so it has 5. Remember, the A group number is the number of valence electrons. So nitrogen has 5, and in this case, it has 1, 2, 3, 4, 5 electrons around it. So if it wants 5 and has 5, it's neutral. Carbon is in 4A. So how many electrons does it want? It wants 4 around it. How many does it have here? Count the dashes as 1, count the dots as 1. 1, 2, 3. It's missing an electron. The charge of something that's missing an electron is positive. This is actually the acylium ion that was talked about in our previous question. Finally, we have oxygen. Oxygen's in 6A, so it wants 6 valence electrons. Count the dots as 1, count the dashes as 1. It has 1, 2, 3, 4, 5. It is also missing an electron. Something that's missing an electron has a positive charge. So we have 0 plus 1 plus 1, which is choice letter B from left to right. Question number 23 says, use the following synthesis of acetaminophen reaction to answer the next 3 questions below. So basically it gives us the amounts of p-aminophenol, the amount of acetic anhydride, and it asks us for how much acetaminophen we can make. So we need to find the limiting reagent, the theoretical yield, and then it gives us an actual yield, and we need to find the percent yield. So that's basically what we're going to do. Now there's not a lot of space here, so I'm just going to have to kind of be creative with where I put the things. But first thing I want to do is let you know that I've made up some abbreviations. I'm going to call this one p-amino. I'm going to call this one acetic anhydride, and I'm going to call this one ACE, just so I don't have to write the whole thing out and make the formulas longer, just abbreviations. All right. So in the case of p-aminophenol, I'm given grams, and I want to know the grams of acetaminophen I can make. So I want to go from grams of p-amino to moles of p-amino using the molar mass, then to moles of acetaminophen using the balanced chemical equation, and then finally to grams of acetaminophen using the molar mass of acetaminophen. So how am I going to do that? Well, I'm starting with 5 grams of p-aminophenol. I want to multiply that by 1 mole on the top and the molar mass on the bottom. The molar mass is given as 109.1 grams of p-amino and on top 1 mole of p-aminophenol times. Now we want to convert it to moles of acetaminophen. Well, notice here, these are all 1 to 1. So for every 1 mole of p-aminophenol in the balanced chemical equation, I make 1 mole of acetaminophen. Then finally, I want to convert it to grams of acetaminophen. So I want to use the molar mass, so 1 mole in this case on the bottom, so moles will cancel out, and on top 151.2 grams of acetaminophen. And when I do all of that math, I get I get 6.9 grams of acetaminophen. I almost wrote the molar mass again. So this may be the amount of acetaminophen we make, but this is how much we can make if we use all of our p-aminophenol. Now we need to figure out how much we can make if we use all of our acetic anhydride. If it's less than this, we can't make this much acetaminophen because we'll run out of acetic anhydride. So in the case of acetic anhydride, I'm going to kind of write the step process over here, and then I'm going to use this little space here to write the dimensional analysis. In the case of acetic anhydride, I'm given milliliters. So I have to first convert the milliliters of acetic anhydride to grams of acetic anhydride, then to moles of acetic anhydride, then to moles of acetaminophen, and then finally to grams of acetaminophen. So the same exact thing, except for the first step is different because I'm given milliliters instead of grams, so I have to use the density, which conveniently is given. So starting with, in this case, 3.0 milliliters of acetic anhydride times, well, the density tells us there's 1.08 grams of acetic anhydride in 1 milliliter of acetic anhydride. Now I need to convert that to moles using the molar mass. So for every 1 mole of acetic anhydride, it has a mass of 102.1 grams of acetic anhydride. Now I can convert from moles of acetic anhydride to moles of acetaminophen using the balanced chemical equation. It's, again, 1 acetic anhydride gives me 1 acetaminophen, so I want to put 1 mole of acetic anhydride on the bottom, so it cancels out, and 1 mole of acetaminophen on the top, so I end up with moles of acetaminophen. The last step's the same. I'm going from moles of acetaminophen to grams of acetaminophen, moles of acetaminophen to grams of acetaminophen, so I can use the same conversion factor. 1 mole of acetaminophen is 151.2 grams of acetaminophen. Multiply by the top, divide by the bottom, repeat till you get to the end, and when I do all that work, I find that I will make 4.8 grams of acetaminophen. So 4.8 grams is less than 6.9 grams. Therefore, 3 milliliters of acetic anhydride, if I use all of it, will give me only 4.8 grams of acetaminophen, and then it's gone. There's no more acetic anhydride. If there's no more acetic anhydride, I can't possibly make 6.9 grams of acetaminophen. This is called the theoretical yield. Acetic anhydride is called the limiting reagent. So, to answer these questions, what is the limiting reagent? Well, it's acetic anhydride because that gives me less acetaminophen. What is the theoretical yield? It's 4.8 grams. Notice that 6.9 grams is a choice, so make sure you do both if you get a question like this on the test. Then finally, what is the percentage yield? Well, here I need to do another calculation. So the theoretical yield is the 4.8 grams, that's what we just calculated. The percent yield, it should be IE. The percent yield is equal to the actual over the theoretical times 100. So in this case, the actual yield is 4 grams divided by the theoretical yield, which is 4.8 grams, we just figured that out, times 100. And when you do that math, you get 83%, which is choice letter A. Number 26 says, considered the ranked polarity of all fictitious compounds with different functional groups is A greater than B, greater than C, greater than D. With A being the most polar, so that's important, I'm going to write it down, most polar, and D being the least polar. So this is the least polar. So, which compound will elute down the column packed with silica gel slowest if toluene is the eluent? Well, there's a couple things we need to notice. We need to notice silica gel and we need to notice toluene. So a couple things about this. Silica gel is the stationary phase, and it's the stationary phase that you guys use in the lab. We also need to know that silica gel is a polar stationary phase. Toluene is the mobile phase, and we also need to know that it is non-polar, right? It's just methylbenzene, so it only contains carbon and hydrogen, so it's non-polar. So what we're essentially looking for is which of these groups will stick the most to the polar silica gel, the one that is the most polar. The more polar the compound, the more it will stick to the silica gel, and the more slowly it will elute down the column, because it asks us for slowest. If it asks us for fastest, it'd be the least polar, but it asks us for the slowest, so it's the most polar, which is compound A. 27, it says consider the TLC of the starting material, SM, product P, and reaction mixture RM after the reaction has been run for 15 minutes. What do these results mean for a reaction known to be irreversible? So first of all, we notice that the starting material travels this far. We notice the product travels this far. And when we elute the reaction mixture, what we find is we get a spot for the product because it has the same RF, and a spot for the starting material, which has the same RF as the starting material. Said another way, that after 15 minutes, the reaction mixture contains both product and starting material. So let's look at the answers. The reaction has not started. Well, that doesn't make any sense. It clearly has started. I see some product. The reaction is complete. Well, this is clearly not the case because I see some starting material. Note that the fact that it's irreversible, okay, means that theoretically I shouldn't see any starting material at the end of the reaction. So since I do see starting material for an irreversible reaction, we know the reaction is not complete. The reaction has started. Yes, I see some product, but is not complete. Yes, I see some starting material. That is the answer. And then the last answer is TLC is not an effective way to monitor a reaction. When in fact, exactly as described here, TLC is an extremely effective way to monitor a reaction, and you had one experience with this this semester. Question number 28 says, what is the major organic product of the sodium borohydride reduction of a ketone? So, we have a ketone, like this, and we reduce it. When you reduce a ketone, we get an alcohol. Reduction like this literally means reduce the number of bonds to oxygen. So we have 2 bonds to oxygen here and 1 bond to oxygen here. Ketones reduce to form alcohols. Alcohol is choice letter A. Question number 29 says, a mixture of ether, boiling point 35, naphthalene, boiling point 218, and biphenyl, boiling point 255, are placed into a distilling flask and attached to a distillation apparatus. Which compound, if any, will distill into the receiving flask first? Well, the compound that's going to distill first is the one with the lowest boiling point, because its molecules are going to have enough energy to boil and then reach the condenser and then fall into the other side on the receiving flask end. So this is ether. You'll note that in this class often you use the solvent evaporator, and a solvent evaporator is essentially a distillation apparatus with a different shape. Okay, it works exactly the same way. It doesn't look exactly the same, but from a what's going on perspective, or it separates things based on their boiling point, and you're boiling off the solvent. Generally speaking, your compound of interest had a high enough boiling point that the solvent evaporator was not capable of pushing it into the receiving flask. Number 30 says, in a Grignard reaction, the ether solvent and all glassware must be very dry. What organic product is formed when phenylmagnesium bromide reacts with water? So, let's say that we don't have any idea how to do this. How might we approach this problem? Well, first of all, it says what organic product is formed. Okay, so magnesium hydroxide is not organic, so that's not going to be the answer. Biphenyl is unlikely to form from a Grignard reagent, so basically your choices are benzene or phenol. So let's look at what we've got going on here. We have phenyl magnesium bromide, and we have water. All right. And again, the most logical choices here are phenol and benzene, because we're going to react these things. Phenol is an OH on the benzene ring, and benzene is just an H here. So how do we decide? How you decide this is thinking about the character of this carbon. Is this carbon partially positive or partially negative? Note that it's bonded to a metal. Metals are extremely non-electronegative. Said another way, metals tend to be positively charged. That makes this carbon partially negative. Once we know that this carbon is partially negative, we need to think about, will it attack hydrogen or will it attack oxygen? Well, in water, oxygen we know is partially negative and hydrogen is partially positive. Opposites attract. So this wants to go after the H, not the O. So what do we end up with? This is the major organic product. Note that there are 5 more H's on here, right? It's C6H6, but this is just benzene. So this is why everything had to be dry, because if you form benzene, benzene will not go on to form the triphenylmethanol, which is what you made in the Grignard reaction. So the last 4 questions are not really questions, they're more of advice of how to study for the final. Before I read these and talk about the answers briefly, I do want to just mention that, one, I hope you enjoyed this course and you got something out of it. There is value in making things, analyzing them, and then trying to figure out if you made what you thought you did. All right, whether you go on to be a chemist or any other type of scientist, or even you don't do any kind of science for the rest of your life, this is a very useful skill. Looking at evidence and trying to draw conclusions from that evidence is important. So I hope you liked the course and I hope you got something out of it. That being said, I do want to give you a little bit of advice, and we did it in the way of questions about how to study for the final. I need to memorize the exact amounts of reagents used in all experiments. We are not going to ask you picky details on the final about amounts used. So to give an example of the borohydride reduction, we want you to know that sodium borohydride is a reducing agent and it will turn a ketone into an alcohol. We do not want you to know how much sodium borohydride you added, how much ketone you added, how long you heated it for, okay, any of this kind of stuff. So, this is not what's important here. What's important is that we understand what's going on, not that we know the exact amounts of things that we use. So don't waste your time memorizing that stuff. Number 32 says, I need to study all of the project reactions because they will be on the final exam. That is absolutely false. Okay, the project is designed so that your team became an expert in your project, but you don't need to be an expert in everybody else's project. That being said, since there's 1 project you need to know and 3 you don't, all right, it wouldn't be fair for us to put those on the final exam, so they're not on the final exam. So don't spend your time on that. Number 33, I need to be familiar with all of the mechanisms in experiments 8 through 12. This is absolutely true. Not only do you need to know what you're going to form as far as the these reactants make these products. So we just give the example of sodium borohydride converting a ketone into an alcohol. You also need to know the mechanism of these reactions. Note that this is like 6 or 7 reactions, and in any given chapter in the latter part of the organic book, there's more than 6 or 7 reactions. So it's not a lot relative to what you need to know for the lecture, but you do need to be familiar with these mechanisms. Some of them you're going to need to be familiar with for the final for the organic exam, I would assume anyway. So I don't think it's extra duty really to need to know them for this. I will say some of these may be first semester reactions. So, all right. Last one, it says, I should be familiar with techniques used in experiments 8 through 12, such as thin layer chromatography, liquid-liquid extraction, distillation, and column chromatography. We did questions on all of these things throughout the practice final, so this is absolutely true. So once again, I hope you enjoyed this course, and I wish you luck on the final, and I hope that this practice final helps you feel prepared, and you go out there and ace the final. All right, thanks for watching.